Hi guys, welcome to another video of Physics 2. This is the problem number 2 about the uniform circular motion. So it says Jupiter, and I'm talking about the planet, has a mass of 1.898 times 10 raised to 27 power kilograms and have an average radius of 69,911 kilometers. And it takes around 10 hours for a complete rotation, okay, and a rotation in its own axis. So we need to find the rotation period, the rotation frequency, the angular velocity, the tangential velocity on the surface in meters per second and kilometers per hour, centripetal acceleration and centripetal force. Okay, so I'm gonna change my screen and I'm going to this over here. Okay, so I'm gonna write the data. We're talking about Jupiter. So Jupiter, that's the planet. Okay, mass equals 1.898 times 10 raised to 27 kilograms. Okay, radius 69,911 kilometers. And okay, rotation period it's 10 hours equals 10 hours. Okay, so the questions, the first question is, okay, the period, the frequency. Remember that the frequency is like with this letter over here, letter C, angular velocity, letter D, tangential velocity, okay, in meters per second and kilometers per hour. And let's see what else. Centripetal ABCDE, centripetal acceleration, and centripetal force. Okay, centripetal force. Okay, so first I'm gonna make the drawing. Okay, so I'm going to consider this as Jupiter. Okay, to me it's gonna be like a circle, and here is the center, here is the radius, and the surface is around here. So let's say, for example, that the rotation is going to be something like this. Okay, that is the angular velocity, so the tangential velocity will be something like this. Okay, that's the tangential velocity. Now, if you haven't seen the video of theory, well, I recommend you to watch it, and I'm gonna put it over here, a card about the theory of the uniform circular motion. Okay, so the first question is that I need to find the period. So if you can see here, over here, well, they give us the period, but remember that I told you that the official units for periods are seconds. Okay, so I need to transform 10 hours into seconds. So in order to do it, well, I'm going to use the conversion factor. So 10 hours, I'm going to transform into seconds. So 1 hour is 60 minutes, and 1 minute is 60 seconds. Okay, this technique that I'm using is the conversion factor. So if you see, hours is going to be canceled with hours and minutes is going to be canceled with minutes. So the answer that I'm gonna get is gonna be seconds. Okay, so let's get the calculator. So it's gonna be 10 times 60 times 60. Okay, so it's going to be 36,000. So the period for Jupiter is going to be 36,000 seconds. Okay, and I'm gonna circle this with red because that is the question number, well, the letter A. And it's kind of impressive if you can see that it's such a big planet. I mean, it's greater than the Earth, and it takes less than 24 hours. That is the rotation period of the Earth. So it's kind of interesting. I mean, there are many other things such as the mass and the gravitational force um, that keep that keeps Jupiter that tremendous or that fast or that little rotation period. Okay, so what about the frequency? Well, if you remember in the previous video, there is a formula that says frequency equals 1 over the period. Okay, so if we find the period, we're going to find the frequency. Now, if you remember the definitions, period is the time that takes an object to complete one full circle or one cycle. Okay, and the frequency is how many cycles this object performs in 1 second. Okay, so this number that we are going to find for the frequency is going to be so small because in 1 second Jupiter is not going to do a full circle. So I'm going to use this equation. So it's going to be 1 over 36,000. 1, 2, 3. And that is the answer. Okay. Another thing that you can do, for example, you can write 36,000, and 36,000 is going to be raised to -1. You can use this key in your calculator only if you want. Okay, that is another choice. So you're gonna get the same result. Oops, you're gonna get the same result. That is going to be that one. Okay, so the frequency, I'm gonna write it over here. The frequency of Jupiter equals, well, 2.7777 times 10 raised to -5. Remember, the official units for frequency are hertz. Okay, so Jupiter makes okay, so if you want to see in a normal number, not scientific number, not using scientific notation, okay, 0.00027 times or part of the rotation in 1 second. So that's nothing. That's nothing, guys. So I'm going to circle this. That is the frequency of Jupiter, frequency for rotation. Okay, that's gonna be letter B. And what I'm going to do, I'm going to save this number in letter A. Okay, because I'm pretty sure that I'm going to use it. Okay, so I'm gonna say that this is saved in letter A of my memory A of my calculator. Now, letter C, I need to find the angular velocity. Remember that the angular velocity is the velocity, the circular velocity is how many radians Jupiter travels per unit of time. So in this case, we're going to use radians per second. Okay, so I repeat, how many radians does Jupiter travel in just 1 second? Okay, so we have, if you remember, we have a lot of equations for the angular velocity. One of them was displacement over time. Okay, so another one was 2p over the period, and another one was 2p times the frequency. Okay, so right now I can use this equation because I have the period, or I can use the frequency, this one, because I already found the frequency. So if I don't want to struggle with the equations, well, I can use the one for the period. Remember, period is the time that takes to complete a full rotation. and the angular velocity is how many radians or per unit of time. So 2p radians, if you remember, 2p radians is a full circle over time. So that's why we use period. Okay, so let's get the calculator over here. Okay, so fraction 2p over the time, there is the period in seconds. Remember, it has to be in seconds, so it must be 36 1 2 3 36,000, and that is the angular velocity. Okay, so the angular velocity equals 1.74 53 times 10 raised to minus 4 radians per second. Okay, and this value I'm gonna save it in the memory B of my calculator. Okay, because I'm pretty sure that I'm gonna need it, and I'm gonna circle this one because this is the letter C. Z. Okay, C. Sorry, C. Okay, so how many radians in 1 second? Well, that's particularly nothing. So let's see. 0.00017 radians in just 1 second. Okay, that's, well, that's nothing. Okay, so next question. Letter D, tangential velocity in the surface. Okay, remember that this is the tangential velocity in the surface, so that's why we're going to need the radius. So if you remember, I'm going to write over here the tangential velocity equations. So tangential velocity equals distance over time, and also tangential velocity equals the angular velocity times the radius, and this is the one that we are going to use. Okay, this is the one. But remember that the problem says that I need to find the tangential velocity in meters per second and then in kilometers per hour. So first let's find it in meters per second. So, okay, I already got the angular velocity. And how much is the radius? Okay, so the radius, I'm just gonna write it over here. Radius equals 69 911 and other 3 zeros because I'm going to convert kilometers in meters. So it's 69 millions of meters. So that's a lot. So I'm going to use that equation, this one over here, in order to find the tangential velocity in meters per second. So I'm going to multiply the angular velocity times the radius, and let's see what was the memory that I used to find the angular velocity is the memory B. Okay, so I'm gonna write that this is in memory B of my calculator. So let's do it. I'm gonna use this equation over here. Okay, so tangential velocity is 69,911,123 times the angular velocity. The angular velocity is saved in my memory B. So alpha B. Boom. Okay, and the answer, the value that I'm going to find is going to be the tangential velocity in meters per second. Okay, so boom. Let's see how much is that. My God, that's a lot. Okay, so I'm gonna write it over here. Okay, tangential velocity equals 12,201.7713 meters per second. Okay, I'm gonna save this value in my memory C of my calculator. Shift STOC. Okay, that means what is the tangential velocity? So imagine that Jupiter is going to stop. Suddenly it's going to stop immediately. Okay, So you are in Jupiter, you are in the surface of Jupiter. So the velocity that you have is the same velocity of Jupiter. So if for some reason Jupiter suddenly stops, you are going to fly. You are going to you are going to get this direction with the tangential velocity of 12,201 meters in just 1 second. So that's incredible. I mean, I'm pretty sure that you are going to, I don't know, uh, well, I don't know if I'm pretty sure that there is no buildings in Jupiter or something like that. But if that happens on Earth, well, um, you will be flying. Okay, you will be flying, and I'm pretty sure that you are going to hit yourself with the wall or something. So imagine yourself at that velocity. Of course, the velocity, the tangential velocity of the Earth, it will be less. It's kind of 1,000 kilometers per hour or something like that. So, well, I guess you will be dead. Okay, so that's meters per second. So now let's find it in kilometers per hour. So let's see, because sometimes we cannot imagine this number if we don't see it in kilometers per hour, because that's a number that we are used to, because we travel and we use the car, and we know that, for example, 100 kilometers per hour, and the school zone is 30 kilometers per hour. So let's transform this. So I need to transform meters per second. So I'm just going to write this, okay? So it's going to be 12,201 meters per second. I'm not going to write the other digits, and I'm going to use the conversion factor, okay? So 1 hour, because I'm going to transform kilometers per into kilometers per hour. So 1 hour is 36,000 seconds. Yes, 60 times 60, I believe. Yeah, 60 times 60 is 3600. Yes, that's it. Okay, and now meters, I got meters here, so I'm gonna write that 1 kilometer is 1000 meters. Okay, so how much is that? Well, I'm gonna write a fraction, use the fraction. This value, I got it in C, so it's gonna be C. Oh, whoa, what did I do? Okay, C times 3600 over 1000. Okay, so that would be the value in kilometers per hour. Jesus Christ, that's a lot. Okay, so the tangential velocity will be 43,926 point 3768 kilometers per hour. That's a lot. I'm sorry, but I'm kind of surprised by this information. Okay, sometimes you just make problems, and sometimes you are used to make problems and you mechanize those problems, and just a few moments, there is only a few moments when you realize the magnitude of those problems. Okay, um, I mean, this velocity is incredible. um, for example, if I want to know if we have reached that velocity, well, of course, we cannot reach that velocity here on Earth, but of course in space. So, for example, what was the name of that? I don't remember. I don't remember the first object that was uh, ejected to the space. Voyager. Okay, Voyager, Voyager, Voyager velocity. Okay, so let's see. Right now the escape velocity was this, okay, velocity, okay. How fast is Voyager 1? Okay, 35,000 miles per hour. Well, you just need to transform that into kilometers per hour, so it will be 49,000 kilometers per hour. Okay, so it's a little bit more than this um, tangential velocity of Jupiter. So that's an incredible velocity. Okay, um, so that's something, guys. I mean, if well, I'm pretty amazed. I'm really amazed for this information. Okay, so let's continue. Let's find the centripetal acceleration. Remember that the centripetal acceleration is the one that makes that you don't uh, go away. Okay, well, in this case it will be the gravity, because we were talking about a planet, but this is a circle. Imagine that you are spinning a rock, something like that. So there is going to be centripetal acceleration, and also we're going to have centripetal acceleration over here and points to the center. So let's remember the equation for centripetal acceleration is angular velocity raised to the square times the radius. Okay, the radius in meters, because the centripetal acceleration, the units are meters per second square. So let's do it. The radius is 69, oh, sorry, 69,911,000 69,911 three zeros times the angular velocity, alpha b raised to the square, and the answer is going to be meters per second square. What? Yes, okay, that is the centripetal acceleration. If you see, well, that's just a little acceleration, okay. Oh, sorry. Yes, sorry. It's okay. It's okay. Yeah, that's the answer. Sorry, I was just seeing some results. I just was seeing if I didn't make a mistake. So the centripetal acceleration is going to be 2.12 96 meters per second square. Okay, so I'm gonna circle this answer over here, and I'm gonna save this value in my memory. I got C, well, shift STOD. Okay, I just want to make sure that I got the real value over there. Okay, so let me make that equation again, because I don't know why I'm so skeptical about it. 911 1 2 3 alpha b raised to the square. Yeah, okay, that is the acceleration. I mean, it's so little the centripetal acceleration. Okay, so this is saving letter D. This is letter D, and this is the letter E. Okay, yeah, it's the letter E. I just wanna make sure alpha D. Okay, now let's find the force. Okay, so there is an equation for force. Force equals mass times the centripetal acceleration, and mass must be in kilograms. Well, let's see if I got the mass in kilograms. Yes, okay, is this number over here, and I'm going to multiply that number times d. Okay, because the centripetal acceleration, I got it saved on d. So, well, let's do it. Parentheses 1.898, and I'm gonna use this key over here, times 10 raised to 27 kilograms. That multiplies the letter D. and that would be the centripetal force. Okay, that's a huge force. So force of centripetal force equals 4.0420 times 10 raised to 27 newtons. Okay, that's a real big centripetal force. Okay, the I, B, C, D, E, F. This is letter F. Okay, so well, this is the problem number 2, and remember we are working with uniform circular motion, so planets are kind of spheres, but if we are watching them in 2D, well, they technically are just like a circle. So we got the mass, the radius, and the rotation period. With that information, we can find everything. So I hope you understood this problem, um, and we are going to continue watching, well, seeing more problems about uniform circular motion. So I hope I can see you in the next video. So take care, guys. Bye bye.